Alrighty, so today is, I guess, our last lecture, even though it's mostly a recitation type review. And so, yeah, like I've been saying for the past couple of times, there's about there are exactly 9 different approaches you're going to want to keep in mind for these Chapter 16 vector calculus questions. And so I figured today we could take a look at the 9 approaches, do one problem from each, where I don't really tell you which one to do. We'll have to go through the whole thought process of how do you decide what to do. So anyway, there's 4 different kinds of questions. There's 2 kinds of line integrals, right? We'll talk about more in a second, but there's 2 kinds of line integrals, and there's 2 kinds of surface integrals. So on the surface, there's 4 main types of questions. But then for some of those, there are going to be shortcuts that happen for special situations. So for line integrals, the first kind of line integral, remember, you have a scalar integrand. And we had this notation d little s. What that did for us was it calculates the mass of a wire. So for example, let's say you have a wire that's made out of some mixture of aluminum and lead, and different parts of it have varying amounts of those different metals. And so therefore some parts of your wire are heavier, other parts of your wire are lighter. And so you could account for that by having your integrand F be the density of different points on your wire. This could also function for, say, traffic on a road. Any kind of quantity that's distributed heterogeneously on a one-dimensional curve. So for example, let's think about the highway. You have your number of cars per mile is sort of the traffic congestion. And so you have your density of cars. And when at certain times there's more cars congested together, that you have a higher car density there. And then other times when the cars are more spread out, you have a lower density. And so anyway, when you integrate this kind of situation, you'd end up with the total number of cars on your road. So and then the second kind of line integral calculates the work done by a force. So this force in this case is our vector field integrand. So pay attention to all these little notational details. This is bold, which means it's a vector field. And the idea is that now your curve represents the path that a particle is taking. And so this type of line integral calculates the work that your force does on this particle when it takes this path. And so essentially, for the first kind of line integral, there's not really any choices. You basically always have to do it directly like we did in 16.2. Whereas for the work type of line integral, there's shortcuts. So there's a special property on the vector field that we're on the lookout for. So remember, certain vector fields are special and are called conservative. Conservative vector field, by definition, has an anti-gradient. So most vector fields don't arise as the gradient of something. But the physical interpretation of this is, not all forces are coming from some potential energy, but some of them are. And when they are, the work done can simply be calculated as the change in potential energy. And so hopefully that's something that you learned or heard about in some capacity in some kind of physics course. And so the idea that the work done is the change in potential energy, the math words we've used to describe that that's the fundamental theorem of line integrals. Okay. And then the next thing we're on the lookout for f dot dr work integrals is special property of your curve. And so it turns out the special property of our curve that we're on the lookout for is whether it's closed. And so closed, just remember, it loops back on itself. It's just a fancy way of saying that the start and the end points are the same. And so when you have a closed curve, you can calculate either a double integral or a flux integral instead. And so in the case that you have a closed curve in R2, that's when you're going to use Green's theorem. If your closed curve is instead in R3, you're going to use Stokes' theorem. And then finally, if your vector field's not special and your curve's not closed, then there's going to be a formula that we can do. It's going to look a lot like this approach up here. But yeah, there are also times when we have to do a direct calculation, like in 62. So it looks like the questions we're asking ourselves here is F conservative? Is C closed? So anytime I see an F.dr question, those are the questions I'm asking myself when I'm thinking about how to proceed. Okay. So same kind of thing for surface integrals. We have our two completely separate types. The first type you want to think of is you have some kind of sheet and you have some kind of density function. So I don't know, maybe I wanted to know how much total ink was used to print out all this text. So the density of ink on the white part is just zero. There's no ink there. But then maybe I have 2 grams per square centimeter of ink where there actually is text. Maybe we're talking about color printing, and so the amount of color ink that you need to use on different pieces of the paper, you could model that by a density function, like the density of how much mass of ink per unit area at various points on our picture, on our piece of paper. And then I guess it's also sort of bent like this. And so anyway, it turns out to calculate the total amount of ink that's needed to print out a page would be basically doing this first kind of surface integral. So again, you want to draw parallels. This is our scalar integrand. And yeah, you want to think of this as a density. I guess I should have write that up here too, that you have either mass density, or in physics, you might be talking about charge that's distributed on some kind of curved plate made out of metal. But it's sort of the same interpretation we've had for other types of integrals in this course, where when you integrate a density function, you get the total amount of whatever that density was measuring. And so, yeah, that's our first kind of surface integral. And then for the second kind, we're talking about the flux of a vector field, which you want to think of flux as essentially how much your vector field is passing through your surface. So for example, if this is my surface S and I want to know flux, I'm sort of asking to what extent are my vector field arrows passing through the surface. So through or across is the key idea. If your vector field arrows are pointing along your surface, that's zero flux. You want to actually be going through the surface to have flux. You could also think about it as if your vector field is the velocity of a fluid, you're calculating the volume flow rate of that fluid through some surface. So for example, if I had my window open and the air was blowing in or blowing out, calculating the flux of the air across the window hole, I guess, right? Because I guess once I open the window, there's not really anything there, but imagine your surface being the rectangle that's occupying where your window would be. That's how you would calculate how much fluid flow in or out of the window. Okay, and so similar to the work integrals, there's going to be some special shortcuts that are appropriate in certain situations. And so the first thing we're going to be on the lookout for is if we have a special vector field. So in this kind, we're saying is F conservative. That's really the same thing as asking work of grad little f. That the definition of conservative is that it's the gradient of something. And so we don't always give you that hint. We're sort of going to leave that up to you here. But we will give you the hint that it is a curl by writing it as curl f. So again, most vector fields aren't the gradient of anything. Analogously, most vector fields aren't the curl of anything. But when they are, that's a special thing, which means that you can actually use Stokes' theorem to either do the work of what you're the curl of, essentially in the language we were talking about briefly the other day, going from curl of f to f, you're doing the anti-curl in the same way that here you're dealing with an anti-gradient. You can either do the work of the anti-curl on the boundary, or you could change your surface to something simpler with the same boundary curve. And so that's sort of the trickiest one. That was last week's material. We'll make sure we talk a lot about that in a few minutes. Finally, we're also on the lookout for a surface that's closed. So in the same way that like a closed curve completely surrounds some stuff inside, a closed surface completely surrounds some bounded solid region in space. And in that case, you could use the divergence theorem. That's what we talked about yesterday. And that's your shortcut there. And then finally, if neither of your things are special, that's when you suck it up and do the direct calculation. So just like before, let's write here the questions we're asking ourselves. So flux of curl F, S closed. So those are the questions we're asking ourselves. So just like how up here we're asking, are we doing the work of grad F? But in this case, it's little f. So again, pay very close attention to what things are vectors, which things are scalars. And that's the idea. So without further ado, let's take a look. We got our 9 questions. And I don't tell you what to do for any of these. And we're going to have to go through and decide. So I'd say the first thing you're going to want to do for this is figure out which one of the 4 subtypes of questions it is. And so you might think that that's, you know, pretty easy, but believe me, I've seen a lot of people get confused and not keep the various main types of questions straight. So let's just do that. So, you know, as you're studying, make 100% sure you could distinguish what is being asked. So this is a, you know, work integral. It's asking about a line integral of a vector field, dot dr. Whereas this is the mass of a wire. So the questions we're going to ask ourselves for this compared to this one are very different. So yeah, let's just go through, do that for all of these. This one is also line integral of vector field. So f dot dr. This one is also line integral of vector field. This one is also line integral of vector field. So I've sort of organized them into the main group. I didn't necessarily put them in order within the various possible shortcuts. This is surface integral of a scalar function. Whereas this, you have a vector field and we're doing flux. Whereas this one, we're doing flux. And finally, this one, flux. So that's the very first thing you're going to want to do for any of these questions. And I know it might sound silly and obvious, but I've seen people get confused. So that's the very first thing to identify. Which of the 4 main types of things am I asking about? Because they're all completely different concepts. Massive wire, massive sheet, work done, flux. So first, figure out which one of those 4 things we're dealing with. Okay. Once you've done that, that's when, for the vector field ones, you start to ask your secondary follow-up questions. That for work questions, I'm looking for conservative vector fields or closed curves. So as soon as I see work, I ask myself, okay, is my vector field conservative? Is C closed? Well, let's figure out about the curve first. C is a line segment from some point to some other point. That does not sound like a curve that's going to then do something and somehow end up back where it starts, right? It just says a line segment. So no, this curve is not closed. Is our vector field conservative? So we didn't review this yet, but remember the test for conservative vector fields is whether, for a 3D vector field involving x, y, and z, is whether the curl is the zero vector. And well, maybe I'll draw our little line here. Nope. So is the curl zero? Well, let's see. Curl F is, remember you do x partial, y partial, z partial of your components. You sort of organize them using our determinant shortcut. So it looks like, no, this is not going to be conservative. Because that's what I get for the curl, and that is not equal to the zero vector. So F is not conservative. So basically what that means is we must do directly with the 16.2 formula. I didn't write it on the previous slides, but the formula you're going to want to remember from that section for this is F of R of t dot product R prime of t. So we have to get our hands on R of t for the given curve. So for line segments, we could do the start point plus t times the end minus the start. So the book writes this a little bit differently. It's the same formula in the book. They just organize it in a slightly less intuitive way, in my opinion. But we could simplify that to 1 plus 2t, 2 plus t, 1 plus t. Okay, and then from here, we just got to do, and so again, for line segments, if you do that, 0 to 1 for t is what you do. And if you're ever a little unsure, you can plug in t equals 0, t equals 1, just to check and make sure. But that's how we do that. And so this then is x, y, z. So we need to do R prime of t is, well, looks like it's 2, 1, 1, right? Yep. F of R of t is, well, F is x, y. So x, y, I'm going to do it out. It's what? 2t squared plus 4t plus t, so plus 5t plus 2. So this is just a little tedious, but not difficult, comma yz. Yz is going to be t squared plus t plus 2t, so plus 3t plus 2. And then xz is going to be 2t squared plus 2t plus t, so plus 3t plus 1. So f of R of t, just replace x, y, and z in your vector field F. Then we do the integral of, well, okay, we could do f of R of t dot product R prime, so make sure you're actually doing a dot product here. So I end up getting, well, 2 times the first component is 4t squared plus 10t plus 4, plus 1 times the second component, plus 1 times the third component, so 2t squared plus 3t plus 1. And so then I'm integrating from 0 to 1. What is this? 4t squared, 5t squared, 7t squared plus 10, 13, 16t plus 4, 6, 7. So I get what? 7/3 plus 8 plus 7. Very quick antiderivative, so 52/3. Okay, so anyway, let's rewind. We first saw that it was a work f.dr line integral. So we were looking for either a conservative vector field or a closed curve. We had neither. So then we use our f of r of t dot r prime of t formula and go from there. Being careful to correctly do our dot product and everything like that. All right. Mass. Scalar function d little s line integral. No shortcuts, right? Go back up here. First kind of line integral, best we could hope for is to do that. So we must do directly like in 16.2, which for this one has f of r of t, but then you have the length of the vector r prime of t. So again, make sure you don't forget the slight difference between the direct formula for the vector field work line integral and the scalar density mass line integral. One, you're taking the dot product with the vector r prime. The other, you're multiplying by the length of that vector. Okay, so now we have to get our r of t. And so a common mistake here is people think that everything could be treated as a straight line, but guess what? It can't. This curve that we're asked about is the part of this y equals cube root of x curve from 0, 0 to 8, 2. So it's not a straight line, so you can't use the line segment formula, but what can we do? Well, back when we talked about this a few weeks ago, the idea was, well, okay, if x is y cubed, then let's be lazy and let y be t so that x is t cubed. And then not everything is 0 to 1 for your t bounds. This is actually going to be 0 to 2. Because check, if t is 0, we get 0, 0 when we plug into r. When t is 2, that's when we get the point that we want, 8, 2. Okay, so now we have to do r prime. We have to do the length of r prime. And then we have to do, well, x ds. X is t cubed. ds is square root 9t to the 4th plus 1 dt. So yeah, this is x ds, 0, 2. Hit that with a u equals 9t to the 4th plus 1 substitution, so that what? 1/36 du is t cubed dt. So I'm left with 1/36. It's going to be square root of u du, so 2/3 u to the 3/2. I'll just plug back in for u. It's up to you how you want to do this, whatever. This should be familiar from old courses. So whatever we end up getting, what is this? 37 to the 3/2 minus 1. Be careful when you plug in. All over 54. That's 3 times 18. All right. So scalar integrand, line integral, you don't have any shortcuts to think about. You just got to do something like this. Okay, next one. It's a work integral. So we ask ourselves, is F conservative? Is C closed? Well, for C closed, we can check what R of 0 is. R of 0 seems to be 0, 0. And R of 2 is what? Well, sine of 4 pi is 0, so I'm going to get 4. But cosine of 4 pi is 1. So I end up getting 4 plus 4, which is 8. So the start and the end point are not the same. Therefore, this is not a closed curve. Okay. For this situation, where we are a vector field only involving x and y, and we only have the two components, the test for conservative was if qx and py are the same. Well, so what's qx? Qx looks like it's 6x squared y. And what's py? 6x squared y. And so, yes, F is conservative. So what does that mean? That means that we find an anti-gradient F. So we want grad F, which of course is little fx, little fy, to equal this vector field that we're dealing with. Okay, and so then that process was you set the x partial of f equal to what you want it to be. You integrate with respect to x. But instead of adding plus c, you add constant with respect to x because we just did the partial antiderivative. So I have to add anything that's a constant as far as x is concerned. So any function involving y is what I could do. Now I differentiate this with respect to y. And I think, well, what do I want that to be? I want fy to be q. So it looks like g prime of y is minus sine of y. So that g is cosine of y. You could do a plus c here, but it doesn't matter. Basically, we found that pq is the gradient of the function x cubed y squared plus e to the 3x plus cosine y. And so now is where you should always check it. There's no excuse for getting an incorrect anti-gradient because just take the gradient, see if it gives you what you want. The x partial of that is p, it looks like, and the y partial is q, so we're good. And so therefore, the fundamental theorem of line integrals says that f dotted with dr is the change in this potential energy function or potential function or anti-gradient, whatever you want to call it, between the start and the end points on this curve. We already figured out that those were 0, 0, and 4, 8. And so you get whatever this ends up being. What is that going to be? 4 cubed, 8 squared, So that's 64 squared Yeah, I mean, so this is a pretty big number. I'm gonna probably not planning on making a deal with something like this, but whatever that ends up being. So 4 cubed, 8 squared, plus e to the 12th, plus cosine of 8, and then be careful, minus 2, because e to the 0 and cosine of 0 are both 1. All right. So we used fundamental theorem of line integrals. Because we had a conservative vector field. All right, let's keep going. Next question. Work integral, f dot dr. Our questions, again, is this vector field conservative? Is the curve closed? So conservative, this is a 2D vector field. I only see x's and y's. So anyway, is this conservative? Qx is 3x squared. Py is negative 2 minus 2y. The answer is no. So not conservative. Is this curve closed? So C is the right half of some circle of radius 2 centered at the origin from 0, 2 to 0, minus 2, followed by the line segment from 0, minus 2 to 0, 2. So what do you know? It is closed. Which means that we will use 16.4, Green's theorem, which says that if D is the region completely surrounded by our closed curve, we do the double integral of qx minus py. So remember, the whole idea was that for closed conservative situations, the work done is 0. This quantity qx minus py, that vanishes. That's 0 when your vector field is conservative. And so in some sense, the work done by any vector field on a closed curve depends on how far from being conservative it is. And so qx minus py is measuring how far this thing is from being conservative. So anyway, it's no coincidence that this thing we're testing for conservative here is what shows up here. But anyway, looks like we get double integral of 3x squared plus 2y plus 2. When you be careful with your minus signs. And what do you know? Tossed in some shortcuts here. This region D that we're dealing with is symmetric over the x-axis, which means that this term, which is odd with respect to y, is going to integrate to 0. That whatever contribution, 2y here is positive, 2y here is negative with the exact opposite value. So when you sort of add them all up and do this integration, the symmetry in the region and the symmetry of the term 2y work against each other, and so you end up getting 0. And then this plus 2 you can easily deal with is by knowing the area of this region. So the quickest way to do this would just be, okay, this 3x squared, I will deal with that, plus twice the area of D. So when I go to do this integration, I'm going to use polar coordinates, so minus pi over 2 to pi over 2 for theta, 0 to 2 for r, 3r squared cosine squared theta, r d theta dr, plus 2 times 1/2 pi 2 squared is the area formula. And from there, I guess, what do we get? Well, 3 times r to the 4th over 4 between 0 and 2. Once you use your half angle formula, which we've done several times, your antiderivative of cosine squared theta is theta over 2 plus sine of 2 theta over 4. And you evaluate that between minus pi over 2 and pi over 2, and then I get plus 4 pi. So what, 16 fourths so 4 times 3 is 12. 12 times, it's going to be pi over 2. So 6 pi plus 4 pi is 10 pi. So again, I guess what I used here also was the fact that these bounds were all numbers and this integrand factored into 3r cubed times cosine squared theta. And so I could do my double integration like that. But if you go through the standard iterated steps, you will, of course, get the same answer. But that's that one. Next one, our last f dot dr line integral. So again, as usual, F conservative, C closed. So it sounds like we have this cylinder around the z-axis and some plane. And this key word here, counterclockwise, I don't use that word if it's just a line segment, because you can't really talk about clockwise versus counterclockwise when your curve isn't closed. So the presence of the word counterclockwise is a huge hint that the curve is closed. And actually, I just realized that I got this previous one wrong ever so slightly. This was clockwise, which meant that Green's theorem comes with a factor of -1. So minus, now fix that. Minus, I'll just change this to minus 10 pi. So Green's theorem is for counterclockwise closed curve. If it's clockwise, no big deal. You just multiply by -1. Okay. So anyway, the word counterclockwise is a hint that this curve is closed. And if you start thinking about this picture, you know, we got some plane, we got some cylinder. The set of points that it has in common is going to be some closed curve C that looks something like that. Okay. So yes. It's closed, but it's in R3, so we're going to use Stokes' theorem instead. And so you might have wondered, like, oh, is it a waste? Should I check for closed curve first, or should I do the conservative test first? It doesn't really matter, because guess what? If it is closed, Stokes' theorem is going to tell us to do the flux of curl F. So if I were to test if curl F is 0, I would be able to recycle that work and use curl F. So yeah, it turns out that curl F for this isn't 0. Let's figure out what it is. So curl F is, what do I get? IJK, X partial, Y partial, Z partial. So I'm not writing them as fractions, just to save a little time. Oh, so this is annoying. I should leave myself some more room. X squared e to the 3x plus y, y squared cosine 2y plus z, e to the z squared plus 2x, y partial, z partial, j, k. So anyway, it looks like I get 0 minus 1, so negative 1. 0 minus 2 there, and then 0 minus 1 there. So anyway, the curl of this is pretty simple, luckily enough. So I'm doing the flux of the vector field minus 2, minus 1, minus 2, minus 1. Okay, and so now I actually have to do a surface integral here. So this is what I'm going to call PQR. I'm going to do my graph shortcut minus PGX minus QGY plus R, where S is given by Z is 3 minus X minus 2Y. That's my G of XY. Because the whole idea with Stokes' theorem is I do the flux of curl F across any surface, any way that I could have soap stuck on this circle C. And then they have to have compatible orientation, so counterclockwise from above for C means upward for S. So that's why I use my upward Z-graph shortcut for this situation. So I put it all together. It looks like gx is minus 1 and gy is minus 2. So I get minus p gx minus q gy plus r, which looks like it's what? Minus 6 dA. And you could set up this double integral in polar coordinates, but why do that when you know the area of this disk is pi 3 squared? So the double integral of minus 6 is negative 6 times the area, so you get minus 54 pi. So this is how we usually like to do these, that if you catch the hints that we're giving you for Stokes' theorem, that it works out pretty damn nicely as far as that goes. That you'll notice, this thing here, this here, this here, those are terms involving X, Y, and Z in each of the PQR components. Those partials don't appear in the formula for curl. So we like to throw things in that go away when you use the appropriate technique. So same thing on this previous example. When you do QX and PY, you get rid of a lot of the scary terms. But yeah, the work of F on a closed curve is equal to the flux of curl F on any surface that's stuck on this thing. So you could have done something crazy. You could have, stuck a hemisphere here, right? You could have stuck a paraboloid shape there. You could have, I don't know, you could have any way that you have soap stuck on that circle before it's detached and you've blown a bubble. But the simplest way you could attach soap to that would be to have S be a part of that plane that we started with. So this is like some of the later homework questions from last week. So second to last homework. This is 16.8. Okay. Let's keep going. So calculate this. So the first kind of surface integral, the two formulas are either f of r of uv times the length of ru cross rv, or if s is given z in terms of x and y, you can memorize what that length of the cross product is going to be. So it's analogous to the scalar line integral situation, where you have the length of some vector here. That's what we have here. The length of this cross product, which in the z equals g of xy situation ends up being that square root 1 plus gx squared plus gy squared. Okay. So anyway, could start to draw this. I know that the x-intercept is 4, the y-intercept is 1, and the z-intercept is 2. So the part of the plane in the first octant ends up just being this triangle that goes through those 3 points. Okay, so which of these two do I want to do? It's up to you. You could write out, r of uv. You could do r of xy. It's up to you. Well, I'm just going to do, the fact that z is equal to 2 minus x over 2 minus 2y, right? If I solve for z in that equation, that's what I get. And this is my g of xy. And then my parameter domain D, it's this shadow in the xy plane, which I already figured out was this. And then I can get going on my formula. Gx is minus 1/2, gy is minus 2, so square root of 1 plus gx squared plus gy squared is 1 plus a fourth plus 4. So 5 plus a fourth is 21/4. So I'm going to get square root of 21 over 2. I'm doing the double integral of z. I have to plug in the fact that z equals 2 minus x over 2 minus 2y. Otherwise, I'm in big trouble, because look at this. My x and y are the variables for the double integral, which means that for my answer to be a number, which it absolutely must, I can't have any z's anymore. So basically z needs to be replaced with 2 minus x over 2 minus 2y. And then finally, I chose to do dx dy because I hate fractions. I looked at this and saw that the slope is minus a fourth, which means that I guess y is 1 minus x over 4, which means that x is 4 minus y. Sorry, 4 minus 4y. So and then, yeah, y goes from 0 to 1. And then from there, it's not so bad. You'll get I don't think we would ask this in multiple choice form just because it's a little bit tedious at this point. But I have my root 21 over 2 out front. My x antiderivative is going to be what? 2x minus x squared over 4 minus 2xy between x equals 0 and x equals 4 minus 4y. And so then I get root 21 over 2. So I get 8 minus 8y minus 4 minus 4y squared over 4 minus 8y plus 8y squared. And then from there, nothing too exciting. I guess I get what? 8 minus 8y, or sorry, 8y minus 4y squared minus, I'm going to leave this as 4 minus 4y cubed. I'm going to do a substitution. U equals 4 minus 4y. So minus a fourth du is dy, which gives me that. And then what? Minus 4y squared plus 8/3 y cubed. Running out of room. But then I just plug in 0, 1, subtract. So I get what? Does that work out nicely like that? 8 minus 8y squared, antiderivative is 8y minus 4y squared, or 8y minus 16/8. So that stuff cancels. I'm going to get an 8/3. At 1, I get 0, but at 0, I get what? 4 cubed over 16. So 4/3. So 8/3 minus 4/3 is 4/3. I think I get that. Did this earlier. Yep, got the same answer. Must be right. Alrighty, but yeah, at that stage, like I said, I don't think we'll leave that behind a multiple choice. Because at that stage, it's just pretty tedious. Alrighty, so I guess let's keep going. So that was the first kind of surface integral. So there were no decisions to make as far as how to proceed. But let's get into the tricky thing. So these last three are the flux situations. And so what I purposefully did here is dealt with very similar surfaces. So you'll notice in all three of these questions, I'm involving this elliptic paraboloid, z equals x squared plus y squared, and then I have the part of it below z equals 9. But we're going to pay close attention to exactly what's being described here. So, like I was mentioning, I guess it was yesterday, that I know that this is tricky, that when you first start practicing these, you're not going to know that you need to pay such close attention. But now that I'm warning you, it should be clear once you stop and think about it and just read carefully each word that's given. So S is the part of the paraboloid below the plane with upward orientation. So it's saying that this is the surface we're dealing with in number 7. It says it's the part of the paraboloid. It doesn't say anything about either a disk on top or it doesn't say it's part of the plane z equals 9. No, S is not the part of the plane z equals 9. S is the part of the paraboloid that the plane z equals 9 cuts off. So there's no top for number 7. And same thing here, that number 8, it's the part of the paraboloid below the plane with upward orientation. So 8 involves the exact same surface. So let's then contrast that with 9. S is the boundary of the solid region above the paraboloid and below the plane with outward. So you got to pay attention to all these little words. S is the boundary of the solid region. So what are the points on the edge of the solid region? Well, you have the paraboloid points that are on the edge. Oh, and that's not going to be outward, sorry. But it also, since the solid region is this, the points on the edge, it also does include that disk on the top. So that's what you have to worry about. So boundary of the solid region will include that top disk. And the word outward is also a hint. I'm not going to use the word outward if your surface isn't closed. I'm not going to use the word upward if your surface is closed. Because the whole idea, maybe I'll write it down here, that upward versus downward are appropriate only for z-graphs, not appropriate for closed surfaces. No, I guess I should say, yeah, always appropriate for z-graphs. They can also work for other types of graphs too, but it's guaranteed to work for a z-graph, and it's guaranteed to not be the correct thing for closed, because closed is, the choices are outward versus inward. That outward, the top has up, the bottom has down. Inward, the top has down, the bottom has up. Either way, you're going to have some blend of vectors that are pointing up and pointing down if your surface is closed. So anyway, outward versus inward is always appropriate. And upward versus downward is never. So yeah, I'm not going to ever use, okay, so you have to be a little bit careful. I could also say that S is the part of Z equals X squared plus Y squared below Z equals 9 with upward, or sorry, downward, and the part of Z equals 9 for X squared plus Y squared less than or equal to 1, sorry, 9, with upward. So I could sort of break apart these pieces and say upward on this piece, downward on that piece. But altogether, the entire thing is outward. So outward means up on the upper part and down on the lower boundary. So I guess you have to be careful. I could refer to downward and upward on various pieces of an outward closed. But it should be fairly clear once you know to look out for this. So like I said, when you first started worrying about this stuff, you probably didn't need to think about all this, the importance of all these things. But now that I've told you it is important, just carefully think about it. It should be clear. Practice a few of these. That, yeah, 7 and 8, I'm not talking about anything going on at the top. It's just the part of the paraboloid below that plane. I don't say it's part of that plane as well. Whereas this one, whether or not it's phrased as the boundary of the solid region, that includes the top. Or if I explicitly say it's both these things together, you know, that's the difference. Okay, so these are all flux questions, like we said. So what do we ask ourselves for flux? Is it the flux of curl F? Is our surface closed? It's a bad question mark. Okay, and so we've thought through some of this when we carefully read about what S was. Number 9, it was, but number 8 and number 7, it was not. So flux of curl F, we will not, unless it's I'd say for a question where you're actually going to do a calculation, we will tell you if it's the flux of curl F by writing it as curl F. So number 8 is the flux of curl F. Now, just because we don't write it like that doesn't necessarily mean that it couldn't be. But remember, being curl is special. And so you might wonder, okay, fine, you didn't write this as curl F, but is ZY3 the curl of something? No, since the divergence of ZY3 is 1, which is not equal to 0. So the test for whether you are the curl of something is if the divergence is 0. It's analogous for the test for whether you're the gradient of something is if the curl is 0. So go back, couple weeks. Same thing here. No, since the divergence of this vector field F that we've given is what? Z squared plus 3z squared x. Remember, divergence is the x partial of P plus the y partial of Q plus the z partial of R. So anyway, no, that's not 0. So this is not the flux of curl F. It's just the flux of some random vector field that's not the curl of anything. So anyway, yeah, that's how you would actually test, is by taking the divergence. But what we'll typically do is tell you it is the curl of something by writing it as curl F. So yeah, this is a big hint that you're going to want to learn to watch out for. Okay. So anyway, I guess let's do the most fun one first, which is the closed one. Flux across a closed surface, divergence theorem tells us it's the triple integral of the divergence over the region completely surrounded by your closed surface. So when I go to set up this triple integral, it's going to be of the function z squared plus 3z squared x. I already took the divergence a moment ago. But then now when you think about, okay, how am I going to do this? I'm going to use cylindrical coordinates where my bottom surface is z equals r squared. My top surface is z equals 9. My r bounds are going to go 0 to 3. When you go through and find the shadow of this, when x squared plus y squared equals 9, that's a disk of radius 3. So r goes from 0 to 3, theta goes 0 to 2 pi. I have z squared plus 3z squared r cosine theta, all times r dz d theta dr. Okay. So this is my z antiderivative is z cubed over 3 plus z cubed r cosine theta r d theta dr, z equals r squared to z equals 9. So I'm left with what? 9 cubed over 3. So what's that? 3 to the 6th over 3 is 3 to the 5th is what? 243, I think. Plus 729. Well, I'm going to write it like this. So 243 minus r squared cubed, so r to the 6th over 3. And then here, times another r plus whatever, 9 cubed minus r to the 6th r squared cosine theta. At this stage, so I gave this in a quiz during the semester where we emphasized more symmetry on triple integrals. We haven't done that so much this summer, so we probably wouldn't do anything like this, but it turns out that that theta integration 0 to 2 pi is going to kill that second term. So that second bit of nastiness over there, yeah, when you integrate cosine theta 0 to 2 pi, you're going to get 0 once you go through that. So anyway, we're left with, I guess, 2 pi times the r antiderivative of this stuff here after you do the theta integration. And so you're going to get what, like 243 r squared over 2 minus r to the 8th over 24 between 0 and 3. So whatever this ends up being, yeah, for non-multiple choice, I don't really care how far people simplify, so we sometimes get these big numbers like this. We're not going to make it do anything like this, but whatever that ends up being. So what is that? 3 to the 243 is 3 to the 5th. So that's like 3 to the 7th over 2. So I have a 2 pi out front. So 3 to the 7th over 2 minus, well, 3 to the 8th over 24 is 3 to the 7th over 8. So basically I'm left with, so like a half minus an eighth is, a half minus an eighth is 3/8. So I get 3 to the 8ths pi over 4 is what that works out to be. I'm pretty sure I did this earlier. Three to the 8th pi over 4 looks good. Yep. I'm good at fractions, apparently. Okay, so anyway, yeah, don't worry so much about that tedious calculation at the end. Big thing is the observation that outward was a hint that the surface was closed, so I wanted to use the divergence theorem. Divergence theorem, you use a triple integral, and be careful, triple integrals, you're not just going to do z goes from 0 to 9, you're going to have to figure out the bottom and top surface, but it should all work out like that. All right, and then I guess these last two, let's do 7 first. For the first one, I'm not doing the flux of curl F, I'm not dealing with the closed surface, so I'm just going to do it directly like in 16.7. So 16, because neither of these worked, I'm going to do 16.7 direct. So the 16.7 direct calculation for something like this, if my surface is a z graph, then that's my minus pgx minus qgy plus r formula. And so that's my PQR up there. My g of xy is there. Aha. I'm just pulling up this answer so I know I'll get it right. Aha, okay, so anyway, let's get going on this. Minus p. So again, at the end of the day, this is a dy dx double integral because I'm doing a z graph which uses x and y as the parameters. So I can't have z anywhere. So this z that shows up in p has to be changed to what it is in terms of x and y, which makes sense. So I get minus p times gx minus q times gy plus r. And so then my region here is x squared plus y squared less than or equal to 9. You can set this all up entirely in polar, or you could be clever and realize that as far as this shadow goes in the xy plane, this is symmetric over the y-axis, which means that this first term that's odd with respect to x, change x to minus x, nothing happens to x squared plus y squared, but 2x has a change in sign, that's going to go away. And so yeah, if you want to be clever with this, you could do minus 2 times this integral of y squared, so that's going to be r squared sine squared theta, r d theta dr once you switch to polar coordinates. And then this plus 3 is going to be plus 3 times, well, the area of this disk, which is pi 3 squared. So you end up getting, well, what? You get r to the 4th over 4, so 81 fourths times 2 is minus 81 halves. The integral from 0 to 2 pi of sine squared, you could go through and do the double angle formula. We've done that 100 times, or just that integral 0 to 2 pi of sine squared theta is pi. So I'm going to get minus 81 halves pi plus 27 pi, which I guess if you care to simplify that is what? 54 minus 81 is negative 27 halves pi. Yep, and that's the right answer. So again, if you're not comfortable with these symmetry tricks for the 0 for certain terms, if you go through, when you go to integrate cosine theta from 0 to 2 pi, you'll get 0 when you do that there. So if you don't see the symmetry at that stage, it'll take care of itself once you do the theta integration. I guess, yeah, that happened. Kind of happened down here, but yeah, I didn't show that step. But when you integrate cosine theta 0 to 2 pi, you get 0. All right. So finally, let's do probably the trickiest one, the Stokes theorem for this, because you actually have two choices here. If it's the flux of curl F, the strategy is Stokes says either do the work of F on the boundary curve of the surface that's given, or the flux of curl F, where S1 is a simpler surface with the same boundary. So you can think about what's going on here. If that's S, the points on the edge of S are that circle. And then what's a simpler surface that's stuck on this circle? That would be S1 is the disk, Z, it's the part of Z equals 9 for x squared plus y squared less than or equal to 9 with upward. So like usually you're not allowed to change the surface. You know, if I ask you the flux across the paraboloid for number 7, you have to deal with the paraboloid for your surface S. But in the special case that I'm asking about the flux of curl F, you are allowed to say, you know what, I'm allowed to change that because it's the idea of surface independence of flux of vector fields of the form curl F. In the same way that we had path independence of work of vector fields of the form gradient scalar function. So this is a big special thing right here. Let's call these 1 and 2. You are only going to do one of these. I'll show you both just so you could see how that would work. I guess if I'm dealing with 1, I need to get my curve R of t going. So let's think about the curve C. Well, it's a circle of radius 3 living in the plane z equals 9, and it's centered at x and y are 0, 0. So that's my R of t for this red boundary curve C. So if I'm doing f dot dr, I need to do r prime of t, so minus 3 sine t, 3 cosine t, 0. I need to do f of r of t, which is 2y, so x, y, z, for x, comma, well, I don't care what this third thing is because the very next step right here is to do f dotted with r prime, and notice the third component of r prime was 0. So whatever. When I do this dot product, I'm just going to get minus 18 sine squared t plus 36 cosine squared t. And so I would do the integral from 0 to 2 pi of minus 18 sine squared t plus 36 cosine squared t. And then I just get 18 pi because I know 0 to 2 pi cosine squared or sine squared are both pi. So you end up getting 18 pi. If you don't remember that, just remember, make sure you remember the double angle. All right, and then if instead I'm going to deal with the flux of curl F across S1, S1 is z equals 9. And so this is the whole power of being able to change this to that, because then I have x squared plus y squared less than or equal to 9, upward. My flux formula is minus pgx minus qgy plus r. And so p, q, and r are the components of the vector field whose flux I'm calculating, which in this case is curl F. But then this gx and gy are 0 because I was changing the surface to be the piece of this plane. So anyway, I just need to get the third component of curl F, which is qx minus py up here. So it's 4 minus 2 is 2. And so then this ends up being the double integral of 2 over this disk, 2 times the area. There we go, 18 pi. So as you can see, you get the same answer, of course. It's up to you which you want to do. That Stokes says you could, for the flux of curl F, either do the work of F on the boundary curve or the flux of curl F across any surface with that same boundary curve. So screw that paraboloid piece. Let's morph that paraboloid piece up into the flat plane S1. And that was our last question. So go through this, go through it again. try to find homework questions, go back, look over the homework from the past few weeks, decide which of these types of problems it all fits into. As you're looking at the sample exams, figure out which one of these 9 strategies they correspond to. 230, it's been up there the whole time, but I think yesterday for the 232 sample exam solutions, I clarified what all questions you guys need to worry about. The 230 final exam is a great starting point, but there's going to be 2 to 3 questions on each of those final exams that are outside of the 232 scope. But I listed on Canvas which questions you should focus on. But yeah, that's pretty much all I had planned for today. And I guess this is the last you'll see of me. So good luck with everything. Enjoy the rest of your summer. Before we take off, you have any questions? I'll stop this recording.